An unitary transformation generated by A as the generator is a mathematical concept in which a matrix A is used to create a transformation that preserves the length of vectors. This type of transformation is called unitary because it satisfies the mathematical property of unitarity. In practical terms, this means that the transformation can be used to manipulate quantum states in a way that preserves their probability amplitudes. Such transformations are important in the field of quantum computing, where they are used to manipulate the states of quantum bits, qubits, in order to perform calculations. They are also used in other areas of physics, such as quantum mechanics, where they can be used to model the behavior of quantum systems. According to the Taylor series formula, we expand the exponential function in the diagram and eventually arrive at a formula that contains matrix A and trigonometric functions. This expression is known as a unitary transformation generated by A as the generator. A unitary transformation generated by the identity matrix is a special type of transformation in quantum mechanics. When applied to a single quantum state, this transformation multiplies the state by a coefficient known as the global phase. The global phase is a quantum mechanical concept that does not have a direct physical interpretation but plays an important role in certain quantum algorithms and measurements. In quantum computing, the identity matrix is often used as a generator for unitary transformations, as it is a simple and easy to implement transformation that can be used to create a variety of more complex quantum operations. To elaborate further, the identity matrix is a square matrix that has ones on the diagonal and zeros elsewhere. It is represented by the symbol I. In quantum mechanics, the identity matrix is used as the generator for unitary transformations, which are transformations that preserve the length of quantum states. These transformations are important in quantum computing, where they are used to manipulate the states of qubits in order to perform calculations. The unitary transformation generated by the identity matrix is a particularly simple one, as it only multiplies the quantum state by a scalar factor. However, this transformation can be combined with other unitary transformations to create more complex operations. For example, by applying a sequence of unitary transformations generated by different matrices, it is possible to create any unitary transformation in quantum mechanics. This is known as the universal gate set for quantum computing. In summary, the unitary transformation generated by the identity matrix is a fundamental building block of quantum computing and quantum mechanics. It is a simple transformation that is used to create more complex quantum operations, and it plays an important role in quantum algorithms and measurements. Pauli matrices are a set of 3 2x2 matrices that are commonly used in quantum mechanics. They are named after the physicist Wolfgang Pauli, who first introduced them in 1927. The 3 matrices are usually denoted as sigma 1, sigma 2, and sigma 3. Each of the Pauli matrices has some interesting properties. For example, they are all Hermitian, which means that they are their own complex conjugates. They also have a trace of 0, which means that the sum of their diagonal elements is always equal to 0. In addition to these properties, the Pauli matrices are also used to represent the spin of particles in quantum mechanics. Specifically, sigma 1, sigma 2, and sigma 3 represent the spin along the x, y, and z axes, respectively. The Pauli matrices have many applications in quantum mechanics and related fields. They are often used to describe the behavior of particles in magnetic fields, as well as to study the properties of quantum entanglement. Each Pauli matrix has 2 eigenvalues, 1 and -1, with corresponding normalized eigenvectors that correspond to the vectors at the intersection of the x, y, and z axes on the Bloch sphere. Let me introduce you to the concept of unitary transformations generated by Pauli matrices. These are a type of quantum mechanical operation that can be used to transform a quantum state. Essentially, they involve applying a series of rotations around different axes, using the Pauli matrices as building blocks. Now, when we say unitary, that means that these transformations preserve the inner product of the quantum state, which is a really important property in quantum mechanics. And because we're using the Pauli matrices as our building blocks, we can create a whole bunch of different transformations that are all unitary. What's really cool about these transformations is that they have a lot of important applications in quantum computing and other areas of physics. For example, They can be used to create quantum gates that perform specific operations on qubits, which are the basic building blocks of quantum computers. So, in summary, the idea of unitary transformations generated by Pauli matrices is all about using these simple building blocks to create powerful quantum mechanical operations that can be used to manipulate quantum states in really interesting and useful ways. Our x can rotate the vector v on the block sphere around the x-axis by an angle theta. Our y can rotate the vector v on the block sphere around the y-axis by an angle theta. Our z can rotate the vector v on the block sphere around the z-axis by an angle theta. Let me tell you about rotation matrices in quantum computing. These are a type of matrix that we use to perform rotations on quantum states. In quantum computing, we often use these rotations to create quantum gates that perform specific operations on qubits. Now, what's really interesting about rotation matrices in quantum computing is that we often use them in conjunction with other quantum gates to create more complex operations. For example, we might use a rotation matrix in combination with a CNOT gate to create a controlled rotation gate, which allows us to perform rotations on specific qubits depending on the state of other qubits in the system. One really important thing to note about rotation matrices in quantum computing is that they need to be unitary, meaning that they preserve the inner product of the quantum state. This is a really important property in quantum mechanics, and it ensures that the quantum gates we construct using rotation matrices behave in a way that's consistent with the laws of quantum mechanics. Rotation matrices are a really powerful tool in quantum computing, and they allow us to perform a wide variety of operations on qubits with great precision and accuracy. They're a fundamental building block of quantum computing, and they're essential for creating complex quantum algorithms that can solve problems that are intractable for classical computers.